Welcome to Quantum, the channel dedicated to exploring all aspects of the quantum world: physics, gravity, philosophy, geometry, computation, and more. Here, we delve into the foundational ideas and cutting-edge theories that shape our understanding of the universe. If you enjoy exploring the quantum world from every angle, whether it's physics, geometry, or even philosophical questions, make sure to like this video, subscribe to Quantum, and hit the notification bell to stay updated. And as always, we'd love to hear your thoughts and questions in the comments below. In this video, we'll journey through the foundational concepts of symplectic geometry, starting with the symplectic form and its connection to Poisson, the language of classical mechanics. We'll uncover the Lie algebra structure of symmetries, which bridges classical and quantum realms, and explore Darboux's theorem, a profound result that simplifies symplectic geometry locally. Next, we'll delve into the cotangent bundle, the canonical symplectic manifold that serves as the stage for classical mechanics, and conclude with a glimpse into how these ideas extend to advanced topics in geometry and physics. Let's dive into the beautiful and unifying world of symplectic geometry. Symplectic form and Poisson brackets. A symplectic manifold is defined by a pair M, omega, where M is a smooth manifold of even dimension, and omega, known as the symplectic form, is a two-form that is both closed and non-degenerate. These two defining properties establish the manifold's symplectic structure. The closedness condition, d omega equals 0, ensures consistency. It means that the symplectic form doesn't vary erratically across the manifold. Mathematically, this is expressed using the exterior derivative, which acts on differential forms and satisfies the condition that applying it twice results in 0. The non-degeneracy condition of omega implies that no vector in the tangent space is left unpaired. This property ensures the form is invertible, but it also imposes an important restriction. The manifold must have an even number of dimensions. This is because an antisymmetric matrix, which represents omega in local coordinates, always has a zero determinant in odd dimensions. Now, let's explore one of the most striking implications of the symplectic form's non-degeneracy: the isomorphism between the tangent space and cotangent space at every point on the manifold. This isomorphism allows us to translate between vectors and covectors seamlessly, much like raising and lowering indices with a metric tensor in Riemannian geometry. Through this isomorphism, the symplectic form acts as a bridge, turning a vector into a one form by contracting it with omega. This operation gives symplectic geometry its power to analyze dynamics, enabling us to connect abstract mathematical structures with physical observables. In the realm of symplectic geometry, every observable, represented by a smooth function, has an associated Hamiltonian vector field. These vector fields are not arbitrary. They are defined by the relation that contracts them with the symplectic form to produce the differential of the observable. These Hamiltonian vector fields have a special property. They generate transformations known as symplectomorphisms. These are diffeomorphisms that preserve the symplectic form. In classical mechanics, they correspond to canonical transformations that conserve the structure of phase space. Symplectomorphisms are the symmetry group of symplectic geometry and play a central role in understanding the invariance of physical laws. The invariance of the symplectic form under these transformations is mathematically expressed using the Lie derivative. For a Hamiltonian vector field, the Lie derivative of omega vanishes, indicating that these flows preserve the structure of the manifold. To fully appreciate symplectic geometry, we need to briefly discuss derivatives. The exterior derivative, Lie derivative, and covariant derivative are essential tools in differential geometry. While the covariant derivative is commonly used in Riemannian geometry to analyze curvature, it is rarely discussed in symplectic geometry. Here, the exterior derivative and Lie derivative take center stage, preserving the antisymmetry inherent to the symplectic form. The exterior derivative ensures the closedness of the symplectic form, and the Lie derivative captures how geometric objects evolve along a flow. This interplay is central to understanding the dynamics of systems in symplectic geometry. Now, let's examine more closely the antisymmetric property of the symplectic form. By definition, the symplectic form is antisymmetric. When you swap its arguments, the sign changes. This fundamental characteristic not only defines the structure of the symplectic form, but also governs the interactions between position and momentum variables. This property is beautifully illustrated through Darboux's theorem, which reveals that any symplectic manifold can be locally simplified into a canonical coordinate system. In these coordinates, the symplectic form pairs position and momentum variables in a way that is both universal and consistent. Furthermore, when we evaluate the symplectic form on two Hamiltonian vector fields associated with smooth functions, the result is the Poisson bracket of those functions. This connection elegantly demonstrates how the antisymmetric nature of the symplectic form underpins the algebraic structure of classical mechanics, linking geometry and dynamics. The symplectic form induces thus the Poisson bracket, a cornerstone of classical mechanics. This bracket describes the interaction between two observables and captures how one changes along the flow generated by the other. One of the most profound properties of the Poisson bracket is associativity, also known as the Jacobi identity. This ensures that the algebra of observables is well behaved, forming a Lie algebra. The Jacobi identity plays a vital role in connecting classical mechanics to quantum mechanics, where it becomes the foundation for the commutator in quantum theory. The Lie algebra of symmetries and quantum observables. In symplectic geometry, symmetry is central to understanding the dynamics of physical systems. These symmetries are represented by vector fields associated with classical observables, which generate transformations that preserve the symplectic structure. Each vector field corresponds to a Hamiltonian flow, defining the infinitesimal transformations of the symplectomorphism group, the symmetry group of symplectic geometry. The collection of these vector fields forms a Lie algebra, where the Lie bracket reflects the Poisson bracket of the associated observables. This algebraic structure connects the symmetries of a system to its dynamics, providing a mathematical framework for understanding how observables interact. In quantum mechanics, the picture shifts. Observables, which are represented as smooth functions in classical mechanics, transition to operators acting on a Hilbert space. This transition is guided by the Dirac quantization rule, which replaces the Poisson bracket with the commutator of quantum operators. This transformation introduces a non-commutative algebra of operators, a hallmark of quantum mechanics. While the Lie algebra of symplectic vector fields encodes classical symmetries as Hamiltonian flows, quantum operators retain these symmetry principles in a fundamentally different mathematical setting, the quantum Hilbert space. The symplectic structure serves as a bridge, translating classical symmetries into quantum behavior while preserving the system's core relationships. This interplay between the classical Lie algebra and the quantum operator algebra underscores the unifying role of symplectic geometry. It provides the framework for understanding how conservation laws in classical mechanics translate into governing relationships between quantum observables, ensuring the consistency of the quantum system with its classical origins. The transition from classical to quantum mechanics is not merely a shift in perspective. It's a transformation of the mathematical language we use to describe the universe. Symplectic geometry, with its rich structure of symmetries and transformations, provides the bridge that connects these two worlds. Darboux's theorem, the equivalence principle of quantization. Darboux's theorem is often presented as a purely mathematical result within symplectic geometry. However, its significance goes far beyond mathematics. It is the foundational principle that underpins what we might call the equivalence principle of quantization, just as the local flatness theorem of Riemannian geometry underpins the celebrated equivalence principle in general relativity. Darboux's theorem states that every symplectic manifold is locally equivalent to a flat symplectic space. In other words, for any point on a symplectic manifold, there exist local coordinates called Darboux coordinates, where the symplectic form simplifies to its canonical structure. These coordinates correspond to generalized positions and momenta, making them essential for understanding phase spaces in classical mechanics. But what makes Darboux's theorem so profound is that it is not merely a mathematical convenience. It is the symplectic analog of the local flatness theorem in Riemannian geometry. In general relativity, the equivalence principle tells us that in a sufficiently small region of spacetime, the effects of gravity can be cancelled out, and spacetime looks flat. This local flatness is the basis for Einstein's theory, connecting global curvature to the local geometry of spacetime. Similarly, Darboux's theorem guarantees that any symplectic manifold, regardless of its global complexity or topology, is locally flat in the symplectic sense. This means that locally, the symplectic structure of any system simplifies to the standard phase space structure, with no local invariance to distinguish one symplectic manifold from another. This universal flatness is what makes the symplectic form so powerful. It is inherently consistent and free of local geometric complexities. Now let's connect this to quantization. The equivalence principle of quantization states that all quantization schemes, no matter how intricate, must ultimately reduce to the canonical commutation relations of the Heisenberg-Dirac algebra. These commutation relations, in turn, are a deformation of the classical Poisson bracket structure, which itself is defined by the symplectic form. In this sense, Darboux's theorem grounds the equivalence principle of quantization by ensuring that the Poisson bracket structure always simplifies locally to its canonical form. The analogy becomes even more striking when we consider the roles of these principles in their respective fields. In general relativity, the equivalence principle bridges local geometry with the global behavior of spacetime as determined by curvature and Einstein's field equations. In quantum mechanics, the equivalence principle of quantization bridges the classical world of Poisson brackets with the quantum world of operators and commutators as determined by the Schrödinger or Heisenberg equations. However, it's important to note a key difference. In general relativity, local flatness is constrained by the global curvature of spacetime, which encodes the presence of gravity. In symplectic geometry, Darboux's theorem ensures that the symplectic form is always locally flat, with no analog of curvature to complicate its structure. This inherent simplicity is what allows the symplectic form to serve as the universal foundation for both classical and quantum mechanics. In summary, Darboux's theorem is not just a mathematical result. It is the cornerstone of what we have called the equivalence principle of quantization. By guaranteeing the local flatness of symplectic geometry, it ensures that all quantization schemes, no matter how complex, reduce locally to the canonical structure of the Heisenberg-Dirac algebra. This parallels the role of the local flatness theorem in Riemannian geometry, which grounds the equivalence principle in general relativity by connecting local inertial frames to the global curvature of spacetime. This profound unity between classical mechanics, quantum mechanics, and general relativity reminds us that the principles governing our universe are deeply interconnected. Darboux's theorem serves as a mathematical and conceptual bridge, linking the classical and quantum worlds through the universal language of symplectic geometry. The cotangent bundle, the canonical symplectic manifold. The cotangent bundle, denoted T star Q, is the archetypal example of a symplectic manifold and the phase space of classical mechanics. It's where the dynamics of systems unfold, connecting geometry with physical evolution. Associated with a smooth n-dimensional manifold Q, called the configuration space, the cotangent bundle collects all possible cotangent vectors at each point on Q. These cotangent vectors, dual to tangent vectors, form the cotangent space. In local terms, T star Q extends the coordinates of the configuration space Q by adding momentum components. Together, the position coordinates Qi and momentum coordinates Pi provide a full description of a system's state in phase space. The cotangent bundle is naturally equipped with a canonical symplectic structure derived from the Liouville-1 form. Its exterior derivative yields the symplectic form, a closed, exact, and non-degenerate structure that governs Hamiltonian dynamics. This symplectic form enables Hamilton's equations, linking the evolution of positions and momenta to the Hamiltonian function, a smooth energy function that generates the system's dynamics. Hamilton's equations describe how the position and momentum coordinates change over time, directly tying the geometric structure of the symplectic manifold to the physical system's evolution. The symplectic form also ensures phase-space volume is preserved during evolution, a reflection of the deterministic and reversible nature of classical mechanics, a result formalized in Liouville's theorem. Additionally, the symplectic form gives rise to Poisson brackets, defining algebraic relationships between observables. Locally, these brackets dictate how position and momentum variables interact, forming the backbone of classical mechanics. The cotangent bundle appears universally across classical systems. For a particle in flat space, the phase space is the cotangent bundle of Euclidean space. For a pendulum, it forms a cylinder with angular position and momentum as coordinates. Even for systems with curved or constrained configuration spaces, the cotangent bundle remains the natural phase space. Finally, the cotangent bundle is the starting point for geometric quantization, where the symplectic structure bridges classical and quantum mechanics. Observables on phase space become operators on a Hilbert space, and Poisson brackets transform into quantum commutators, preserving the system's structure in the quantum realm. In summary, the cotangent bundle is not just a mathematical construct, it's the universal stage for classical mechanics and the gateway to quantum mechanics. Summary of the remainder of the lecture. In the remainder of the lecture, we'll explore the advanced elements of symplectic geometry, including its topological and homotopy properties and its relationship with Riemannian geometry. We'll delve into how symplectic manifolds and Riemannian manifolds become unified in Kähler and coadjoint orbits, allowing us to transition consistently to twistor spaces and non-commutative geometry, offering new perspectives in mathematical physics. Finally, we'll introduce Poisson manifolds as a generalization of symplectic geometry, highlighting their role in systems with constraints and their connection to quantum mechanics. Thank you for joining us on this journey through the fascinating world of symplectic geometry. From understanding the symplectic form and Poisson brackets to exploring the Lie algebra of symmetries and the foundational role of Darboux's theorem, we've seen how these concepts bridge classical mechanics and quantum theory. The cotangent bundle, with its elegant symplectic structure, highlights the universality of this framework, while the connections to advanced topics like quantization and non-commutative geometry hint at the vast potential of symplectic geometry in modern physics and mathematics. If you enjoyed this discussion, don't forget to like, share, and subscribe. We'd love to hear your thoughts and questions in the comments below. Thank you for watching, and we'll see you in the next video.